The test article is a 27.5-foot diameter, 20-foot tall aluminum-lithium orthogrid cylinder, very similar to the types of cylinders that we're flying on the Space Shuttle external tank. In fact, this test article is derived from some excess hardware from the Space Shuttle program. So it's configured very much like the future SLS core stage tank structures, so it's very relevant to what NASA is designing today. In this test, we're going to be trying to simulate a lot of the same types of loads that a launch vehicle would be subjected to during flight. That includes internal pressure associated with the fuel tanks, as well as flight loads that you would see, and that would include compression type forces and bending forces, similar to what would happen if you crushed a beverage can under your foot. The black and white polka dot pattern you see on the outside of the test article is used in a system called digital image correlation. And what that system does is we have a series of 22 cameras surrounding this test article, and it's monitoring during the test minute movements of these dots, and from that calculating the displacements of the test article. It's a really powerful type of technique that allows us to watch displacements of the test article during the test on the entire structure, because traditionally we would only get point measurements, a single gauge here, a single gauge there. For something this large, the digital image correlation system really gives us a lot of good information. The NESC, NASA's Engineering and Safety Center, is the primary sponsor and funder of this project. They saw very early on the need to update these design guidelines, and I came to them with a proposal to form this project, and so they've been the primary funder. The primary stakeholders would be people like SLS, as well as commercial crew, and then industry at large. We have a large following of industry partners that come to workshops, and we discuss a lot of the data and discuss their needs as an industry. So this project, I think, is going to have a large impact in the long term, not just NASA and SLS. Well, we had several visual cues of this thing buckling. We look at data to see that it's buckled. We have our digital image correlation data that's streaming real time for us that indicated, even before buckling was occurring, that the buckling was anticipated. But we can also view the test article outside of our control room window, and we have it positioned in such a way that we can see it buckling at the time. And so it was quite dramatic. We could see it buckle, we heard the bang.
The shell buckling test has been conducted at Marshall Space Flight Center because inside of our load test annex, we've got one of the largest tensile test machines in the world. We've got a movable crosshead that weighs 3 million pounds and can react 30 million pounds of axial compression, making it perfect to do large-scale structural tests. It's an indoor facility, which makes it ideal for the video image correlation systems that we use to monitor real-time strain distributions during actual load events. The Space Launch System consists of 5 major components: the forward skirt, the liquid oxygen tank, the hydrogen tank, the inner tank, and the engine section. I'm going to be the lead test engineer for the forward skirt and the liquid oxygen tank. One of the biggest examples of how this directly affects the Space Launch System is we're learning on real hardware that's the same size as, for example, the forward skirt. A matter of fact, the shell buckling test article is the same diameter as the forward skirt, and it's a little bit taller. So we've got a real-life test article that we're practicing on, we're learning, and we're helping provide good data to the NESC.
And lift off.